Hello friends, welcome back in the video lecture. Today we will see the titration curves part of this volumetric analysis. In this there are four main types of titrations that we have to see, and these are titration of strong acid and strong base, then titration of strong acid weak base, third one is titration of weak acid strong base, and fourth one is weak acid weak base. Okay, so let us start. The first one is the titration of strong acid and strong base. We have to see the examples of strong acid and strong base. How the titration curve can be obtained for this strong acid and strong base titration. Okay, so here we have chosen the strong base as 0.1 normal sodium hydroxide, that is NaOH, and the strong acid is 0.1 normal hydrochloric acid, that is HCl. Okay, so for the titration we know that what are the requirements, what are the glasswares. We know that we need a burette, we need a calibrated pipette, then conical flask, then all these solutions. Okay, so these are the basic requirements for the titration. Okay, actually this is the theoretical part we are considering for the titration of strong acid and strong base. Okay, now here we have a choice. Which solution should we take in burette and which solution should we take in pipette? The choice depends on us. You can choose by your own, but generally it is trend in the world that generally the best solution is generally taken in burette and the acid solution is generally taken in pipette. Okay, or a solution of which the concentration the solution of known concentration is generally taken in burette, and the solution of which the concentration we have to determine is generally taken by pipette. Okay, here there is no any determination of strength of acid or base. Simple, we are determining the titration between the strong acid and strong base. Okay, so the solution in burette is 0.1 normal 25 ml 0.1 normal NaOH. Okay, it's a strong base. 0.1 normal 25 ml 0.1 normal sodium hydroxide, that is NaOH solution in burette, and we have taken by pipette in conical flask 0.1 normal HCl. So in this case, as this hydrochloric acid is monobasic acid and NaOH is monoacidic base, all are monovalent, so that's why the normality and molarity of these two chemicals is one and the same. So that's why if in our next calculation, if there is M instead of N, there will be no any change, or normality or molarity of these two solutions will be same in this case. Okay, so that's why we have to determine the titration curve for this two chemicals, for the strong acid and strong base. Here the graph is shown, and this graph is showing the titration curve. Okay, titration curve of HCl and NaOH, both are 0.1 normal. So this graph is nothing but a plot of pH versus volume of NaOH added. So we are adding sodium hydroxide from the burette in the conical flask. In the conical flask we have taken the 25 ml 0.1 normal HCl, that is hydrochloric acid, we have taken by pipette in the conical flask. Okay, and we are adding the sodium hydroxide, that is base, from the burette. In this case, this NaOH, that is base, is a titrant, and HCl, that is acid, is titer or titrant. Okay, so that's why this is the graph of pH of the solution in the conical flask versus ml of the 0.1 normal NaOH, that is base added from the burette, and this graph is showing the nature of the titration curve for these two chemicals, for this strong acid and strong base pair. Okay, so you can see here the pH is changing from 1, 2, 3, 4 up to 12, and we have taken on the graph that is volume of NaOH added 5 to 30 ml. Okay, so you can see the nature of this graph is like this. It is starting from the 1 pH. Okay, this up to pH 3, there is gradual increase, and it is a straight gradual increase in this pH of the solution. Okay, and after this 3 pH, the pH of the solution at 25 ml of NaOH is we are adding, the nature of the graph changing from, and it becomes vertical. So up to 3 to 10 pH units, the nature of the graph is vertical, and after 10 it is again becoming a parallel to the y-axis, that is to the volume of sodium hydroxide added. Okay, and after some time when we are trying to when we are continuing the titration, then it becomes downward. Okay, so in this case, so the equivalence point is in this range between the 3 to 10 pH units of the graph. Okay, and in this case, which indicators are having their transition range? So there are 4 main indicators are having their transition range in this range of pH units, and these are methyl red is having 3.1 to 4.4, then methyl orange indicator is having the pH range or transition range in the from 4.2 to 6.3, then bromothymol blue is having the transition range from 6.0 to 7.6, and phenolphthalein indicator is having its transition range from 8.3 to 10.0. So all these 4 indicators, methyl red, methyl orange, bromothymol blue and phenolphthalein, all these 4 indicators can be used, so that can be used for this titration, because their transition range is from 3.1 to 10, and our equivalence point is also in the same range, that is 3 to 10 pH values. Okay, so that's why all these 4 indicators can be said to be are suitable indicators for this titration. Okay, so all these 4 indicators are suitable indicators, but what is the best indicator? So the equivalence point of this titration is near to 7. Equivalence point of this titration is near to 7 pH. So that's why which indicator has its transition range near the 7 unit of pH. Okay, and it is only one, that is bromothymol blue. It is having transition range 6.0 to 7.6. So that's why the bromothymol blue is the indicator which can said to be the best indicator for this titration of strong acid and strong base. Okay, now for this titration we have to calculate the pH at different stages of the titration. We have to determine the pH at the different stages of the titration. In your examination of the university exam, out of these three, one titration may be asked for long answer type of question. Okay, so that's why it is important from the exam point of view, how to what is the nature of this graph, then what are the suitable indicators, then which is the best indicator, and how to calculate the pH of the solution at different stages of the titration, that we have to determine here. Okay, so let us start to solve, let us start to calculate the pH of these solutions of this titration during the course of this titration. So there are in your text the number of calculations are given, 5 to 6, 7 calculations are given, but there is no any need to write or to calculate all these pH values for this titration. For any titration, let us say only 3 to 4 calculations are sufficient. Mind well, or remember well, only 3 to 4 calculations are sufficient to calculate for the pH values for any titration curves, okay, for any titration pair, whether it is strong acid, strong base, weak acid, strong base, anyone, okay. So no need to draw or no need to calculate all the values, all the pH values, okay, because it is time consuming and it's a long answer type of question. So let us start. We have taken, for your convenience, for this first type of titration, we have taken the 4 calculations of pH values, and the first one is the pH of the solution at the start of reaction. pH of the solution at the start of the reaction. So initially, before going to start the titration, okay, so what is the situation now? So keep in mind that is we have taken burette, and in burette we have taken sodium hydroxide 0.1 normal 25 ml sodium hydroxide NaOH solution is taken in burette, okay, and in conical flask we have taken 0.1 normal 25 ml SCl solution by pipette. With the help of pipette we have pipetted out that SCl solution and we have taken in that in conical flask, okay. And before going to start the titration, we have added we have to add some indicators, okay. So and we know that all these 4 indicators are suitable indicators, but the best indicator is the bromothermal blue, okay. So here we are not determining actually the which indicator we have to add here, and what is the color or of that indicator in acid condition and in basic condition. There is no need in here, only we have to calculate the pH values, okay. So before starting of the titration in conical flask, we have only SCl solution, that is hydrochloric acid solution, 0.1 normal SCl solution, okay. So the concentration at the start of reaction or titration, we have only 0.1 normal or molar, you can say same, molarity and normality of SCl is same here because it is monobasic acid, 1 molar SCl solution, okay. And means we do not added sodium hydroxide from the burette yet. Still we have not added the sodium hydroxide NaOH solution from the burette. So this is at the start of reaction, okay. So this is the concentration of H plus ion. So H plus ion concentration is nothing but 0.1 molar, that is equal to 10 raised to minus 1 molar. In 10 to power, this 0.1 molar is nothing but 10 raised to minus 1. This is known to us now. How to convert this, that we know as well, okay. 10 to power minus 1 molar. Now what is the formula of pH? pH is equal to minus log to the base 10 of H plus ion concentration, that is nothing but log to the base 10 of 1 upon H plus ion concentration, that is equal to log to the base 10 of 1 upon, what is H plus ion concentration? It is 10 raised to minus 1. 1 upon 10 raised to minus 1, it becomes log to the base 10 of 10 raised to 1, and 10 raised to 1 the value is, so therefore pH is equal to 10 raised to 1 is equal to 10 raised to 1 is 10, so log of 10 to the base 10 is equal to 1, okay. So log of 10 to the base 10 is equal to 1. So the pH at the start of titration is 1. So the pH of solution, so here the solution is only SCl in our conical flask, we doesn't added any sodium hydroxide from the burette, so we have only acid SCl, and hence the pH is 1, means it is strongly acidic in nature, okay. And we know that the pH range is when it is 1 to 6.9, it is acidic, and as pH is 1, it is strongly acid, and that's why we know that SCl is a strong acid, so that's why pH is 1 at the start of reaction. Now second one is the pH of the solution, when 5 ml of Yes, 5 ml of 0.1 molar SCl added, sorry, 0.1 molar NaOH added in 0.1 molar or normal 25 ml NaOH solution. So this is the condition. Now we in our conical flask we have already what? We already have, sorry, HCl. We already have hydrochloric acid solution. It is 25 ml. We have already taken by pipette 0.1 molar 25 ml SCl solution. We have already taken it, and we have started titration. You can add 1 ml, 2 ml, 3 ml, okay, or drop wise, but for our sake of convenience we have now taken for the calculation. When we are adding 5 ml of the sodium hydroxide from the burette in the conical flask, which is already having 0.1 molar 25 ml SCl solution, then what will be the pH? So in this case, the hydrogen ion concentration, we have to calculate the pH, and for the calculation of pH we need H plus ion concentration. So H plus ion concentration in this case is equal to millimoles of H plus ions divided by total volume in ml. This is the formula to calculate the H plus ion concentration. So millimoles of H plus ions divided by total volume in ml. Now how are the millimoles of H plus ions? Now in this case, this is the case before equivalence point. This is the case before equivalence point, and before equivalence point there are more H plus ions. There are more H plus ions because in conical flask the acid is 25 ml, SCl is in 25 ml, and from burette we have added only 5 ml base. Okay, so nothing. It's mean that acid is more in conical flask, means that H plus ion concentration is more. So that's why to determine the H plus ion concentration we have to solve this like this. Millimoles of H plus ions, how will you calculate that? Millimoles of acid taken, millimoles of acid taken minus millimoles of acid taken minus millimoles of base added divided by same total volume of solution in ml. Okay, now millimoles of acid taken, how will you calculate? The molarity of acid is 0.1, and what is the volume of acid? It is 25. Okay, minus millimoles of base, the concentration is 0.1 molar, and what is the volume of base added? 5 ml. Okay, divided by total volume. First the acid taken is 25 ml plus base added from the burette is 5 ml, so it is 25 plus 5 is 30. Okay, so 0.1 into 25, 2.5 minus 0.1 into 5, 0.5 divided by 25 plus 5, 30. So what is the sum? It is 2.5 minus 0.5, 2 divided by 30. 2 divided by 30. The answer of this is, we are calculating H plus ion concentration. So answer of this H plus ion concentration is equal to it is approximately 6.67 into 10 raised to minus 2. 6.67 into 10 raised to minus 2. You can solve this by calculator. So 6.67 into 10 raised to minus, this is nothing but H plus ion concentration. Now pH is equal to log to the base 10 of 1 upon H plus ion concentration, and it is equal to log to the base 10 of 1 upon 6.67 into 10 raised to minus 2. Okay, and the pH of this solution becomes 1.176. You can use your calculator or Calci for solving this. Okay, no need to remember all these figures. Okay, just these figures, these numbers are important. So pH of the solution at the when we are adding 5 ml of the 0.1 normal or molar NaOH solution to this conical flask, the pH becomes 1.176. pH becomes 1.176. Okay, see now I have to calculate two more pH calculations. So that's why I have to rub these two calculation now. Okay, because there is no space on the board. I am repeating again these two calculations, how to calculate. Okay, so let us see again the pH at the start of reaction. So at the start of reaction only acid is there in conical flask, no base is added. So in conical flask we have only 25 ml of 0.1 normal HCl solution, that is acid solution. So the concentration is this. So H plus ion concentration is equal to 0.1 molar, that is nothing but 10 raised to minus 1 molar. Okay, so pH is equal to minus log of H plus ion concentration to the base 10. Okay, it is equal to, simply rearrangement of this equation is taken. So it is minus, so that's why I have taken reciprocal of this. So that's why minus sign get cancelled. Okay, is equal to log of 1 upon H plus ion concentration is 10 raised to minus 1, and that is 10 raised to minus 1. Again 1 upon 10 raised to minus 1, reciprocal 10 to power plus 1. Okay, simple is there. And 10 to power log of 10 is 1, log of 10 to the base 10 is 1. So pH at the start of reaction is 1. Then pH when we have added 5 ml of sodium hydroxide, that is base, from the burette to this acid solution, then what will be the H plus ion concentration? H plus ion concentration is equal to millimoles of H plus ion divided by total volume in ml. Total volume in ml is nothing but, previously we have 25 ml HCl and we have added 5 ml NaOH from the burette. So 25 plus 5, it becomes 30. Now millimoles of H plus are calculated by using millimoles of acid base, acid taken minus acid is previously there, minus millimoles of base added, means H plus ions are consuming by the base that we are adding from the burette. Okay, so that's why all these things should be taken into consideration. So they can be calculated by concentration into volume 0.1 into 25 minus concentration of base 0.1 into base. Okay, so 2.5 minus 0.5, 2 by 30. So answer will become 6.67 into 10 raised to minus 2, and pH is equal to, by keeping this value in this formula, we get 1.176. Okay, so when we are adding 5 ml of NaOH, still our equivalence point is not reached, because equivalence point is near the 7 pH. Okay, and pH becomes here 1.176, means it is still acid in the strong acidic range. Okay, so that's why now I have to rub this, because I have to calculate two more pH values for this titration curve. Now the third point is the pH of the solution when pH of the solution at the equivalence point, at the equivalence point. At the equivalence point. At the equivalence point. So at the equivalence point, the pH can be calculated is equal to 1/2 of pKw. 1/2 of pKw. In SYBSc we have learned all these things. Okay, so what is pH and pK value? pKw. pKw is, what is pKw? The Kw is equal to ionic product of water, Kw. It is 1 into 10 raised to minus 14. This is at 25 degrees Celsius. Means at room temperature, the Kw value, ionic product of water, is 1 into 10 raised to minus 14. So that's why pKw is 14. pKw is 14. So therefore pH is equal to 1/2 of pKw. pKw is 14. So therefore pH is equal to 7. At the equivalence point of titration between strong acid and strong base, the pH of the solution becomes 7. Okay, very simple. Then the fourth calculation is remaining, and this fourth calculation is the pH of the solution. This is third. The pH of the solution when 26. What is meant by equivalence point here? Means we have taken 25 ml of HCl in conical flask with the help of pipette. Okay, and both are strong acids, HCl and NaOH. Both are monobasic and monoacidic acid base pair is there. Okay, so to neutralize completely the 25 ml 0.1 normal HCl, we must theoretically we must need 25 ml 0.1 normal base, that is NaOH. Okay, so means the pH at the equivalence point, and at the equivalence point, what is the volume of NaOH added? It is 25 ml. Look at this, 25 ml. So at the equivalence point means when we are adding 25 ml of the base NaOH from the burette, what will be the pH? And this pH will be 7. Look at this. This is 7. Okay, so this point coincides with this 25 ml of NaOH and 7 pH. Okay, this point is locating at the straight line region of this curve. Okay, this is most important part that one should remember. Now the pH of the solution when 26 ml means at equivalence point we have already added 25 ml of sodium hydroxide, that is base from the burette. Now we are adding 1 ml more than the equivalence point. So after equivalence point we are adding 1 ml more base from the burette to the conical flask. Then at this stage what will be the pH of the solution? Okay, so 26 ml of 0.1 molar NaOH added. So in this case, now at equivalence point both H plus ions and OH minus ions combined together, the neutralization reaction will take place, and there is a formation of neutral sodium chloride, that is salt, and water molecule will be formed. Okay, so at equivalence point all the solution in the conical flask will be in neutral condition because the pH of the solution will be 7. So no more excess of H plus ions and no more excess of OH minus ions are there in the solution. But when we are adding 1 more ml of NaOH, in this case obviously equivalence point is this is the case after equivalence point, means the base is more in conical flask because the volume of acid taken is fixed, that is 25 ml. It is get neutralized by the base 25 ml 0.1 molar NaOH is there, it is get neutralized, and after equivalence point when we are adding 26 ml 1 more ml after equivalence point, there will be OH minus ion concentration in the solution in more excess. Okay, so that's why we will calculate the concentration of OH minus ions first. Concentration of OH minus ions. Why? That I already explained this. How will you calculate millimoles of millimoles of OH minus divided by total volume in ml. Okay. Then how will you calculate this? Millimoles of OH minus will be millimoles of base added minus millimoles of acid taken, reverse of the case second, millimoles of base added minus millimoles of acid taken. The denominator will be same. The millimoles of base added, so concentration is 0.1, base is taken 26 ml minus 0.1 into millimoles of acid taken is 0.1 into 25, acid is taken is 25 ml, it is fixed. Okay, so 0.1 into 26, 2.6 minus 0.1 into 25, 2.5. 2.5. Okay, so my answer becomes this is total volume in solution 26 ml of NaOH plus 25 ml of acid, a combination of both these two. Okay, so 26 plus 25, it becomes 51, and this calculation will become 2.6 minus 2.5. The answer will be 2.6 minus 2.5, 0.1. 0.1 divided by 51. 0.1 divided by 51. Okay, so the answer will be OH minus ion concentration here. Here is also OH minus ion concentration. OH minus ion concentration. Okay, so the concentration 0.1 divided by 51, it becomes 1.96 into 10 raised to minus 3. 1.96 minus 1.96 into 10 raised to minus 3. This is the OH minus ion concentration. You can solve this by using calculator. Now this is OH minus ion concentration. How will you convert into POH? So POH is equal to log to the base 10 of 1 upon OH minus ion concentration. Okay, so by putting the value of this OH minus ion concentration in this equation, the POH will become 2.71. Okay, you can solve this. So now we have to calculate the pH. So this is pH. So what is the relation between pH and POH? I can write here. So pH plus POH is equal to 14. Now we have to calculate pH. So pH is equal to 14 minus POH is equal to 14 minus what is POH? It is 2.71. So therefore pH is equal to 11.29. So pH of the solution, when we add 26 ml of NaOH from the burette, the pH will become 11.29. See this. This is very important. Up to equivalence point, when we have added 25 ml of NaOH, that is base, from the burette in the conical flask which has 25 ml of acid. Okay, the strength of concentration of both the solutions is same. Okay, up to this the pH is 6. When we move from 25 ml to 26 ml, that is just 1 ml more from the equivalence point, the pH of the solution increases drastically, increases very fastly from 7 to 11.29. From 7 to 11.29. So at this stage. Okay, so this drastic change in pH can be observed. Drastic change in the pH value can be observed when we are adding just 1 ml extra more the base from the burette. Okay, so this is nothing but the theoretical background before of the titration of strong acid and strong base. We have taken here HCl as a strong acid, 0.1 normal, and NaOH, that is sodium hydroxide, as a base, which is also 0.1 normal. Okay, so this is the theory behind this titration. Okay, so this is most important part of this titration. Nature of the graph, how it is looks like, then choice of indicator, okay, which is the suitable indicator, which is the best indicator, then 4 points you have to remember how to calculate the pH values of the solutions in this titration. Okay, so I think you got it properly. Okay, see the video 2 to 3 times, then you will learn about what is the actual theory behind this titration. Okay, thank you very much. Have a nice day.